Alrighty, in this video we want to talk about calorimetry. This is a pre-AP topic that we're going to squeeze into AP as well, so this video is kind of for everybody. To start this off, I want to go through some basic thermodynamics concepts. Now, thermodynamics is just the study of energy and energy transformation, energy movement. There's lots of parts of thermodynamics, and we're focusing really on just the first two laws of thermodynamics here. They're both very simple. And we apply that directly to calorimetry. So first of all, in this box over here, we have a few important notes. Heat is a form of energy. Okay, so heat has nothing to do with how hot something is or cold. Those are just relative terms. Heat has to do with the motion of particles in a substance. We talked about how if the particles are moving fast, like in a gas, they have a high temperature. We translate that to meaning it's holding a lot of heat, a lot of energy. So heat is just a form of energy that flows, and it flows from high temperature to low temperature. That's known as the zeroth law of thermodynamics. That's the very basic concept. You know that if you touch like a hot frying pan, it burns you because the energy flows from the frying pan, which is at a very high temperature, to your hand, which is at a much lower temperature. And then the process of burning has to do with overcoming chemical bonds. But the energy is flowing from the hot substance to the cooler substance. And no matter what the temperatures are, as long as there is a difference in temperatures, then you're going to have this heat flow. You may put two things into contact. One of them may be at minus 50 degrees Celsius, and one may be at minus 80 degrees Celsius. They're both quote-unquote cold, but heat will still flow from the warmer one, minus 50, to the colder one, which is minus 80. So heat flows from high temp to low temp all the time. Heat will always flow until there is no more difference in temperature. We call that point thermal equilibrium. If you touch something that's the same temperature as your hand, it's like you can't even feel it because it's the same. There's no flow, there's no energy change. Other than texture and pressure, you wouldn't even know it's there. So that's the zeroth law of thermodynamics and its consequences of heat flow. Now, this energy that flows between something hot and something cold, we have a term for those things. We have a system and surroundings. Now, a system is a very loose definition. A system can be anything. For example, if I have a beaker full of warm water and I put a little penny in it, the system could be the penny if I define it that way. The system could be defined as the penny and the water. The system could be defined as the penny, the water, and the beaker, or the system could be defined as the entire room. So really it's up to the observer to define what the system is. When we do calorimetry and most experiments, we want to define the system as narrowly as possible. So if we were doing this, what we're going to do is keep it narrow. So if we were doing a math problem with this, we would say that the system was probably going to be the penny, and then everything else would be the surroundings. Surroundings in any case are anything that's not defined within the imaginary border of the system. If you look at the picture over here, you have a good concept of this. We're showing the system to be some object or some area within this border. It could be a block, or it could just be the reactants of a chemical reaction. So we put this in here. If this is the system, that means everything else is the surroundings, including the water, the container, the thermometer, and even outside of this container. So the system, in this case, is very narrowly defined. If we go to the next bullet point, this is very important. This is really the basis behind calorimetry. Energy is always conserved. We call this the first law of thermodynamics. So what this is really saying is that if the system, or any system, loses heat, I'll show that with an arrow here, that energy doesn't just disappear, it doesn't just go away. Something else has to take that energy up. In this case, it's broadly defined as the surroundings. So if energy leaves a system, the surroundings get it, an equal amount. If the surroundings lose some energy, and the system then has to gain an equal amount. So there's always an equal interplay between the system and the surroundings. You've learned the two terms for this before. We call that endothermic and exothermic. Endothermic, of course, is when the system gains energy, and exothermic is when the system loses energy. We usually associate exo with something getting hot, but that's because you are the surroundings. And if you are experiencing an exothermic chemical reaction, for example, the reactants, the system is losing energy. It's going out into the surroundings where you are, and you are feeling that, and you are gaining it. So you are the surroundings, and that's why you feel it as your temperature going up, or you feel it as hot. The endothermic reaction would be the opposite. You are the surroundings, and you are having to put energy into the system to make it go, so to you it feels cold because you are losing energy and the system is taking your energy and soaking it up. The basic idea behind calorimetry is this little equation here on the last bullet. The heat lost, that's what Q stands for, heat lost equals the heat gained by something else. The little negative sign out in front here is just a mathematical thing here. I'll explain it more in a minute, but it doesn't matter which side you put this on. The math will work out either way. I had just always put it next to Q lost because lost is exothermic, and as you've probably realized from some of the early calculations you've done before, maybe even in middle school, exothermic is usually a negative value of heat. So I went ahead and put the negative sign in front of the negative number. These Q's come from our very basic, most important equation in thermodynamics, well, at least in the first part of thermodynamics. Q equals mc sub p delta T. This is the heat capacity formula. We're going to do some practice problems with it also. But we can calculate the amount of heat required to make a certain temperature change. That's what delta T stands for, temperature change. And it's all dependent upon one physical property of the substance, is known as the specific heat. So Q is heat capacity, C sub P is specific heat. They're very closely, they sound a lot alike, they're very closely related. Let me give you the definitions of each, and then you'll see it again on the handout. Q, the heat capacity, is defined as the amount of energy required to make a substance go up by 1 degree Celsius. Or in other words, change the temperature by 1 degree Celsius. The specific heat is the amount of energy required to raise 1 gram of the substance by 1 degree Celsius. So the only difference between the two were the words 1 gram in this term right here. That's what makes it specific. In science, anything that's specific refers to a per mass, a per gram unit. Okay? So we'll go through it again. Q, which is heat or heat capacity, can be found by taking the mass, multiplying it times this intensive physical property called specific heat capacity, times the change in temperature. And down here I just rewrote it again as with delta T expanded to final minus initial temperature. And we always keep it final minus initial. Some teachers teach changing this around depending on whether you're the system losing or system gaining, and I find that too confusing. So I fixed this little problem by having this negative sign in front of my calorimetry formula. So that's why I put a negative sign. It lets me always use this formula, and I never have to switch it around or exchange initial and final. Just use this formula right here. You may wonder how this is useful to you at all. Let me just go through real briefly how this is used in normal everyday life. This little picture here is a very simple calorimeter, but this is the process that chemists use to figure out the calorie content of any food you eat. Let's just say it's a cracker, and you know, if you look on the back of a Ritz cracker box, it'll tell you how many calories are in one Ritz cracker, or maybe sometimes two, but just for the sake of argument, let's just say one Ritz cracker. What chemists do to determine that number, remember calorie is just a English unit of heat. The metric unit is joule, but the old English unit is calorie. Of course, we still use calories in this country, especially for food. But what they would do to figure out that heat value is they would put the cracker inside of a reactor called a calorimeter. That's what the meter stands for, a measuring device. And the system would be the cracker, which is an organic compound, carbon, hydrogen, oxygen, maybe some other stuff. And we burn it with oxygen. So that's the system, the cracker plus oxygen. We burn it, and it gives off a heat. It's exothermic. That heat escapes, just like I have shown here, and is surrounded by water. So scientists measure the temperature change of the water. From the temperature change of the water, the known specific heat capacity of the water, and the mass of the water, they could figure out how much heat was given off by the burning of the cracker. So they can go in and calculate the heat capacity, the molar heat of the cracker, and turn it into calories. That's what they do for all food. They use a calorimeter. Let's do some practice problems with this.